Hi everyone, thank you for joining me on this student tour. My name is Marwah Osma and I'll firstly begin by introducing the cluster and the themes relevant to it before beginning the tour of my Team and Ice project. So the project that I'll be discussing is from Research Cluster 8 of the Architectural Design Program taught by Kostas Grigoriadis and Martina Rosati. The cluster's main focus is multi-materiality and how new material mixes can have the potential of creating hybrid conditions that can have structural, optical, and assembly advantages. We then had to apply this hybrid material onto a large-scale architecture, which was the main concourse of Houston Station. So for the 2019-2020 cohort, we had three groups in the cluster, each focusing on a particular material mix. We had the metal and glass fusion group, the clay and glass fusion group, and our group, which looked into 3D printed multipolymers. So I'll now begin the tour of the project, which is called Metaplast 3D Printed Multipolymers, and it is by Betty Chavez Angeles, Papertsoen, also known as Sai Leitluv Chachai, Wisnu Hardziantia, and myself. The show is divided into four sections. Section 1, which focuses on the multipolymer foldable panel. Section 2, which shows the digital and spatial approach. Section 3, the pattern, color, and lighting approach. And finally, Section 4, which is our architectural scenario. So as you first navigate through our show, you see a glimpse of the final material system, which is a close-up detail showing the intricate folded system that we developed. But before delving into more of the final outcome, we wanted to show some of the overarching concepts as they relate to the advantages that a decentralized system can offer in terms of ecology, equity, and economy, and how a 3D printed multi-material system can benefit these three sectors. As our site is Houston Station, we then mapped the entire process of recycling, 3D printing, and assembly within a radius from the site. In terms of materiality, we were interested in the advantages and potential of a continuous and multi-material system disposing of inherent structural characteristics and able to be 3D printed flat and folded once printed. This was achieved through the use of two recyclable thermoplastics, which were mixed according to specific ratios corresponding to the level of rigidity and flexibility required. The folding, as you can see, especially on the right, was achieved through an integrated patterning system. And below is a larger scale version of the folded multi-material system. So the next step was to observe how we can begin to stabilize the folds within the continuous surface. We decided to opt for a cable network which is strategically located in areas requiring the most structure, thereby adding another layer of stiffness. In this drawing, we see the rigid to flexible material gradient distribution of the two thermoplastics, which shows how they were mixed in different ratios in order to obtain the fold. The next part of our show is the digital and spatial approach. In the first image here is a close-up of the digital folded mesh and cable network we developed. In order to achieve this, we first began by understanding the logic of the fold through digital simulations and by investigating the structural capacities of different patterning systems. In the end, we developed a unique customized process which involves the use of structural analysis prior to applying the folds. This results in the red areas which require the most structure to be densest in folds, while areas that are bluer will have sparser ones. After analyzing the effect of gravity and elasticity on the structure, we applied tension through the cable network that we developed earlier. We placed the cable network in the reddest areas of the structural analysis so that it provides adequate tension to hold the folds together while also adding further local stiffness. We also considered the relationship between the structure and the ground through separate 3D printed parts attached to the mesh through a laminating technique. As discussed earlier, our approach involved a decentralized production model, and as you can see here on the left, we divided the structure into panels able to be distributed to different facilities within a radius from the Houston Station site, directly relating the distribution of the panels to their size and to the scale of the production facility. The parts are then assembled through a snap lock system as seen on the right, which eases assembly, maintenance, and disassembly. Overall, this assembly system minimizes the use of structural elements, which reduces weight, cost, and fabrication as well as assembly time. So the next part of the show is the pattern, color, and lighting strategy. Further research has gone into integrating thermochromic plastics, which are plastics which change color according to temperature. We sought to make further use of the multi-material 3D printing technology in order to embed these micropatterns. The aim was to achieve passive control over the lighting temperature for interior spaces, which can improve overall well-being while also using lighting as a didactic tool able to guide people through the interior spaces. And here you see a top view of the material system, and below is an isometric drawing which shows the material system as it is applied on the digital prototype. Here we see a close-up and exploded version of the thermochromic stack involved in the passive strategy to control the interior Kelvin temperatures within the panels. In this exploded axonometric, we see the 6 layers involved in the final multi-material system. The result is an intricate folded mesh with a layered composition which serves both the structural and material requirement and the color, pattern, and lighting intentions, while also exhibiting unique spatial qualities as you can see in this interior perspective. Finally, I'll be discussing the architectural scenario, which is Euston Station. Here you see a top view close-up of the new Euston Station design with the material system application. And for the design, I'll play this video. So for the design, a circulation-based design was applied through the use of evolutionary algorithms. The aim was to improve permeability and interchangeability through the optimum positioning of entrances and platforms, and by finding the shortest paths between them, while also considering the positioning of programs and public spaces, as you can see here. We then applied our customized structural process as seen in the exploded drawing on the left before adding the cable networks and ground connection, which you can see on the right-hand side. Finally, we applied the micro patterns for the Kelvin temperature control of interior spaces, adding further texture and intricacy to the system. The proposal showcases a material system developed, Metaplast, in the context of a large-scale architecture through the redesign of Euston Station. And the final image is the aerial view of the canopy of Euston Station illuminated at dusk. So with this final image, I think that's it for Metaplast Student Tour. Thank you for tuning in and joining me on this tour. I hope you enjoyed it and hope you also enjoy all the other great projects on display. Thank you very much.
Hi everyone, welcome to the Bartlett B-Pro show. My name is Jackson. I'm from Research Cluster to Master of Architectural Design, which led by Stefan Bessing and Federico Borello. I'm currently an architect at Zaha Hadid Computational Design, and I'm pleased here to introduce you to our project on behalf of my teammates Ding Yifan, Yu Yingying, and Han Su. Our cluster RC2 focused on the utilization of industrial manufacturing techniques and the conjunction of developing architectural products. We have been exploring how design and geometric development are driven by materiality, manufacturing constraints, and fabrication sequences. This focus allowed us to investigate existing techniques and develop our own, studying how process becomes an important driver in delivering data from the digital to the machines, establishing a direct relationship between digital input and physical output in various architectural scenarios. My project for the last year was called MFAB, Incremental Metal Fabrication. It explored the architectural product applications of robotic incremental metal sheet forming and polystyrene insulation that adapt wide variations in complex geometries and modular structure. My project is in the shape of a product company, that provides a synthesis of services, including robotic fabricated products, architectural application, and construction. Founded upon the innovative fabrication techniques, the product we designed and prototyped specializing in dwelling and infrastructure applications across a range of scales that integrate embedded service functions, cost-efficient manufacture process, fast assembly, customizable kilopod, and game engine interaction platform. The project is closely aligning with and complementary to the robotic fabrication, digital design, and distributed project delivery method. In the past year, my team worked closely with BMate staff on a number of fabrication techniques, from robotic metal forming, polystyrene steaming, as I mentioned, shotcrete, welding, metal milling, etc. And we also designed a set of self-invented tools to help the design and fabrication process. Hundreds of tests, experiments, and prototypes along this journey, which all merges into 4 individual products: canopy panel, acoustic ceiling, floor tile, and partition. Each of these 4 products has specific qualities aligned with their practical functions and design features expressed through the unique fabrication techniques we explored. At the micro scale, the fabrication development as the foundation of our project was considered from several aspects, which is what we believe where architecture design meets product design, such as the haptic detail like patterns and textures on the finished product, assembly details, how these details allow us bringing these outcomes into construction reality that differentiates from how similar projects or similar structure got built in the conventional methods. And also the build qualities that integrate several materials, several techniques, and several products into one space that meets functions, performance, and aesthetic. For the second half of the project, we brought the outcomes and product to a larger scale, to the architectural scale, introduced 3 applications as the testing grounds for our product to evolve in specific conditions. The first application is a residential retreat. So part of this residential retreat is a web browser-based configurator developed through a game engine. This configurator is supported by our kilopod design strategy, which allows end user or client or constructor to engage with the design process and personalize architecture as a product in terms of space quantity, material specifications, product combination, or any personalized demands. The second application is designed for market infrastructure. And the third application is for camping site planning. So these 2 large-scale applications considers a planning strategy in a generative way, which promotes the kilopod product to adapt architectural mobility and space arrangement in the flux. In the process of making to design, my project has traveled across scales, contains material study, fabrication techniques, prototype, architectural application, customization, sales strategy, and construction. The theme of our research cluster, manufacturing-led design, introduces this innovative methodology and envisions the role of architects as a combination of designer, maker, engineer, and even enterpriser. That's it for my project and a brief introduction to my cluster. Thank you very much for checking it out and hope you enjoy the rest of the show.
Hello everyone, my name is Maaya Harakawa from RC1, and now I'm speaking from Tokyo. Today I will talk about my project. First of all, Research Cluster 1 is run by Deborah Lopez and Hadin Chapel. It explores monumental Westland, which focuses on speculative climate immersion and post-anthropocenic assemblages. It seeks anthropocenic scenarios through the lens of the ubiquitous production of data, extraction of raw material, and reliance upon logistical processes, considering the impacts that these practices have on contemporary conditions. The series focuses on the Arctic territories currently experiencing permafrost thaw as a result of warming temperatures. If you'd like to know more about our RC, please check this video. In RC1, there are four teams: Team Human, Team Non-Human, Team Earth, and Team Logistics, which is our team. I worked with 3 members, Rammo, Natapo, Pimpasak, Jinwan, towards our project Decommissioning Svalbard. Decommissioning Svalbard is operated in Longyearbyen, Svalbard, Norway, where is the world's northernmost island town inside of the Arctic Circle. The town is considered as an island of paradox. The city wavers between ecological and geopolitical importance as a remote island of Norway that need to be inhabited to secure the country's sovereignty over the Svalbard archipelago. High avalanche risk in the main town, which is increasing due to by climate change paired with strict environmental law, has created the housing shortage and puts the city in limbo. This project aims to mitigate this contradictory situation through hypertypologies, hybridized buildings that retain architectural essence of the past while adapting the new demands. The methodology employs machine learning material detection and binary code, with voxelization referred to as voxel version. Let's go back to bPro show. Firstly, this cover page shows how we define nostalgic factor of a church in Svalbard. Nostalgic factor is one of the important aspects of our project. That is why we put this image here. The project is separated into 4 sections, from research and classification to a final output. The first section, an island of paradox, introduces the process of material detection and cataloging. In section 2, it shows how the project understood and proposed the architectural space in a digital way. Also, it explains the way to voxelize the target building for hybridization to tackle the high avalanche risk. Section 3 is about architectural optimization from voxel to architecture by using a material catalog. In the last section, it shows a final model of the building, movie, and global scale case study. Then let's move on to each section's detail. As I've told, section 1 is about machine learning material detection and cataloging. The first one is a scene of an automated process of building decommission. At the same time in this stage, the project detects architectural member and material through machine learning, because we propose to reuse abandoned material for new constructions. To do so, the project used these hundreds of interior and exterior images as a dataset. After these 2 processes, the detection result and the material itself are kept as decommissioned material, as a decommissioned material catalog. We propose 2 types of catalog. The 3D one helps the user to choose material intuitively, and the 2D one can compare each material's property. Also, it shows material member utilization. Through these various steps, decommissioning building are digitized and cataloged. This is an image of digitization. In section 2, the project proposed hybridization of the building, dealing with an area shrinking of the town due to the high avalanche risk. Like this image, we boxerize and hybridize the target buildings. As a case study, we choose a local church, restaurant, and clinic as a target. And the drawing shows an image of how voxel transformed to architecture. After the boxerization, the project defined several criteria to analyze architectural space based on its character to keep the original architectural essence even after the hybridization. As you can see, each voxel is applied its binary code with color based on its spatial character. So the diagram is result of voxelization and application of binary code towards target buildings. We call it as a voxel version. Sorry, this one. As I've told, target building is chosen from avalanche hazardous zone. The movie is described this method. This is a result of hybridization, which is executed based on the binary code. The left one is a 3 typology hybridization, church, restaurant, and clinic. And the right one is just church and restaurant. Thus the size, shape, and complexity are different. As a way to hybrid needs various constraints, this page explains the logic of hybridization. Next section is about an architecture optimization from voxel to architecture. It introduces how the voxel version is applied material from the catalog. It shows all process from decommissioning to reaggregation of the building based on the binary code. The drawing tells the decommissioning result and its cataloging data. By using this cataloging data, the next one draws materialization and architecture optimization process based on the catalog and the binary classification. Next two diagram and images show the final voxel version and its materialization. It is constituted to be the final voxel version based on multiple criteria, such as binary code, location, and the target building's architectural essences. Material application also needs multiple criteria. And finally, this is a result of aggregation process, which is our final building. Although it's different from the past, the local people might feel some nostalgic feeling from its material and spatial atmosphere. Section 4 shows a final building and a global case study. The project speculates at a worldwide scale on other contexts, where the tension between profit-driven societies and environmental destruction has resulted in the recently dubbed phenomenon of crime migration. This is a scene that the project is executed in Indonesia. The project starts to keep dismantled material, same as Svalbard project. And the next one is another final building's interior drawing. This is an audio video of our project that speculates a future town in Longyearbyen. You can see the image of final building detail like this in this video more. Thus, I would recommend watching this as it tells all steps of our project. The next drawing tells our planetary scale research and case studies. Though the methodology are the same, the final result and its architectural expression is different, as the material and, let's say, the essence of architecture is fluctuating, depends on the place, culture, climate, and so on. Overall, the project responds by exploring how the decommissioning of building parts can be combined with nostalgic factors to create new architectural outcomes. It lies somewhere between preservation, novelty, and the representation of place identity. We believe our project was able to propose an opportunity to reconstruct climate issue and the lifespan of materials. Also, it might bring an innovative way to tackle the growth society to see current profit-driven world critically through the Internet of Building Things. Thank you for listening and enjoy BPro Show. See you.